welcome to another video. In this particular video, we'll rather be looking at a worked example, or we'll be working out an example on the electrostatic force. Right, so we'll just do one example for this video. Now, let's get to it. So imagine you are given this problem. So in this particular scenario, you have three charges. You have Q1, Q2, and Q3, right? So what happens here is two of them are positive, which is Q2 and Q3, and one of them is negative, which is Q1. All right, so we're given the diagram and we're given the distance between their respective charges. Right, they are placed at right angle to each other as shown below. So this is a right angle. That's what it means, right? So now, remember with charges or with these units, right? One thing before we continue is that 1 microcoulomb is simply 1 times 10 minus 6 coulomb, and 1 nanocoulomb is 1 times 10 minus 9 coulomb. There's also something called picocoulomb, but you'll rarely see it. That's 1 times 10 minus 12 coulombs. Right, it's important to convert, especially once you start plugging in these values into your formulae. Right, so that's one thing I wanted us to note before we continue. Now, so this is a past paper problem from, obviously, a past paper. It was question 7 in that paper. Right, so the first question that we're asked is, state Coulomb's law of electrostatics in words. So one thing you'll notice that typically in each question, when it comes to physics, there'll be a definition before. Usually it's the first question that you'll meet, and then following that are calculation questions, right? So definitions, in some cases, they may contribute up to 13% of your final mark, right? Assuming you get every one of them right. Or their weight, the relative weight of these types of questions. So always know your definitions. 13% is quite a significant amount of marks, right? So let's get to it. So Coulomb's law simply states that if you have two charges, right, and obviously they are emanating an electric field, and as a result they are exerting an electrostatic force on each other, right? So this force that they exert on each other will be directly proportional, right, to the product of the charge's magnitude. So for instance, Q1 times Q2, the force will be directly proportional to that product, and then inversely proportional to the square of the distance between them. So if I take this distance between Q1 and Q2 and I square it, my electrostatic force is inversely proportional to that, which means if I increase the distance, the electrostatic force magnitude will decrease. And then if I decrease the distance, the magnitude of the electrostatic force between Q1 and Q2 will increase. That's what inversely proportional means, right? So you would write that for 7.1. So officially you would say the magnitude of the electrostatic force this thing is a bit too thick. Okay, let's try that one. Of the electrostatic force, okay, let's do this, exerted by 1 point charge, still thick. You can call this charge Q1 or Q2, right, on another point charge, which is, okay, this is Q1, and then the other point charge is Q2. It's a very long definition. Well, when I write it, it looks long, but it's actually very short when you memorize it. Now this is where now you say it's directly proportional right, and then to the product of the charges. Of course, you have to say magnitude, because when you say charges, it means something else. No, not magnitudes. Okay, it's fine. Of the charges. Suddenly looks like a huge paragraph. I promise it's not that long. It's just that the way I'm writing my words, or rather, the size of my screen. And inversely proportional to r squared. That's what we say. To the square of the distance between the Some people prefer writing symbols as they write this, like they would say something like this: r, square of the distance, then they write r between them. It's up to you. You don't have to. So it's typically given by the equation F is Q1 Q2 over r squared, and then you have your electrostatic constant there. Right, this is how we typically write the equation for the electrostatic force, or Coulomb's law of electrostatics. Right, and then next we are asked to just find the net electrostatic force on charge Q2 due to charges Q1 and Q2. Okay, I think there's a mistake here. I think Q2 charges Q1 and Q3 is what they meant. Right, so because this is Q2, this is Q3, they mentioned both Q1 and Q2, so we'll assume they meant Q3. It was probably corrected during an exam, hopefully. Otherwise, that was going to be a huge blunder. So now we have 7.2. So what I like to do is split these two things. So first you have the force on Q2 due to Q1. That's scenario number one. Then you have the force on Q2 due to Q3. Let's start with the force on Q2 due to Q1. Right? Now let's do it. So we know, let's call it F1. Of course, one would say F1 on 2, something like that. But let's just call it F1 to have a short subscript. It will be K, Q1, and Q2 in our case. All this divided by r squared. Right? Then you sub in 9. Then you have 28, that's Q1, times 10 to the negative 9, and 32. Notice I do not include the signs. The signs of the charges, I don't include them. That's typically how you do it for electrostatic force. There's no need to include the signs. Of course, if you're using another method, it might work, but for the method I'm using here, there's no need for the signs. All you have to do is interpret the final answer. We'll get to that though. So 30 divided by 1000 should be 0.03 is precisely. Right, then we want to find the answer to that. 99 times 28 times 32, and divide all of this by the square of the distance between them. On my side, I get 0.0896 newtons. Right, that's my force. So this force Q1 on Q2, right? If you check Q2, you'll have something like this. Let's say this is Q2. Due to Q1, Q2 will obviously experience attraction. So it'll be going that way. The force F1 will be pulling Q2 towards the charge Q1, because these are unlike charges. So as a result, you'd have something like this. So we can say this force is going, or is pulling Q2 that side to the left, but I don't think we have to specify it. You normally do that for charges, but force is also a vector. In an event where you have to specify it, this would be to the left. Right, so then you have force on Q2 due to Q3. So you see, we are breaking it down so we understand what we're doing for each case. Right, then we have this guy. Let's call this one F3 because it's from the charge 3 or Q3. Call it K, Q2, Q3 because we are focusing on Q2 and Q3 now. And then we have R squared. We still have 9 times 10 to the power 9. Q2 is 32. Q3 is 36 nanocoulombs. Nano is to the power 9. Right, and then we have our distance between them being 0.04 all squared. So we can find our answer for this one as well. It will be 9 times 32 times 36. 0.04 squared. Okay, 0.00648. The reason I'm not rounding off now is because I haven't reached my final answer yet. So for this one, if you check, you'll have, let's say this was Q2. Due to Q1, there'll be a repulsion. So Q2 will be repelled up. Right, so we can say F3 it may be upwards. Right, so now let us find the free body on Q2 so that we can determine our resultant. If this is Q2, right, due to Q1, we'll have a force a component of force going that way, right? The black dot is Q2, by the way. So let's call this F1. And then let's zoom in. And then there'll be, due to Q3 will repel Q2. So there'll be another force. Let's make it purple, of repulsion, which we called F3. Now, if you notice, we have two components now. This forces us to have a 2D resultant vector. So our F net is a 2D resultant vector. So it means now we have to use Pythagoras theorem. And then this is our theta, some call it theta r for resultant angle, right? So, or the angle of the resultant vector. Now let's try and find that, because the question asked us to find the resultant force. So let's come into it here. So if you check, these things are arranged such that it's a right angle triangle. And if you check this is our right angle triangle. So we have the hypotenuse, which is F net. We have the adjacent, which is F1. And we have the opposite, which is F3. So we can say F net is essentially, according to Pythagoras theorem, F net squared is F1 squared plus F3 squared. Obviously, we have to square both sides so that we find F net. So F net, or the net force, is F1 squared plus F2 squared. So we have F1 and we have F2. So we said F1 was 0.00896. F2 was 0.00648. From here, we can find our answer. This is 0.011 newtons. So now remember, a force is a vector and it deserves a direction. We have to specify a direction. So since it's a 2D vector, unfortunately, we cannot just simply say left or right. Reason for that, it's basically in two directions. It's going up while also going to the left. So we need to find that angle, right? Because the net force is just diagonal, and a diagonal vector means it's covering two directions at once, the up direction and the left direction in this case, or the vertical direction and the horizontal direction. So that's why every time you see a 2D vector, you have to specify the direction. So we use tan in this case. Say tan theta. Let's call it theta r. Obviously, it has to be y over x, or some call it opposite over adjacent. It's up to you. Let me zoom in. Now, which one is the opposite side and which one is the adjacent side? So basically, our F3 is the opposite to theta r, right? And then adjacent to theta r is F1. That's our tan theta r. Therefore, theta r is just tan. Then we can substitute. F3 we said is, oh sorry, I made this F2. This is F3. We said F3 is 0.00648 and F2 0.00896. So therefore our theta, let's check our theta r. We find that our theta r is 35.87 degrees. So this is how you do a question like this one. So whenever you see a 2D vector, remember the way you would specify a direction for a 2D vector is by using an angle. And since we have the adjacent F1 and the opposite side F3, we can take the ratio of that and use tan to find angle theta r, right? So that's what you would do. So this one, we said this is our this thing is Q2, by the way. So we're just drawing the free body diagram at Q2. All right. Thank you for watching. Catch you on the next video.